Hello everybody, my name is Andreas Fertig. I work as a trainer, software developer and consultant, and occasionally as a speaker. And I'm extremely happy to speak to you today because the topic of the talk is C++ Insights, and I happen to be the author of C++ Insights. No fire alarm, excellent. So, you all have been, or more or less all have been, in Herb's talk this morning where he was talking about that whenever you develop something, may it be software, hardware, whatever, and you need to put a sign on it, tell people what they should do with it, the design intention may not come across to them. And he showed this example of the Nero Cafe, and when I arrived here at my hotel, I experienced this in the elevator. It seems that you may not be able to read it, but there is something you can put your card in, and the sign says you need to put your card in there to operate the lift. I guessed that, but probably there are some people who are not familiar with that. I don't know. So, and what they decided to do is to be really safe, so they put another sign on top of it. Slightly different phrase, but essentially saying the same. Put your card in there to operate the elevator. So I did, for 3 days. At the third day, in the evening, I realized the person getting in the elevator with me on the other side, same elevator, just pressed. And so it came, and maybe it was still activated because of my card. And then I realized that is how the other side looked. No place to put a card in, no signs. So then I learned I do not need this card. So for the ongoing time, I didn't put it in there anymore because it's obviously not needed. Until I tried to get up from the breakfast room on Sunday morning. Elevator seems to be broken. Pressing didn't help. So I reached out for help, and then they explained to me, yeah, well, you know, in several cases, we shut it down overnight, so then you need the key card to operate it. So thank you. There's a sign missing telling me when to use it and when not, but all right. Enough about that. Let's talk a little bit about languages, and the first language I'd like to talk today about is German. I'm German, and my last name is very German. It's a frequently used word in German. It's Fertig, and you can translate it with finished, ready, complete, or completed. That's excellent for a project name, right? It ought to be a member of some team. Some people think then the project will finish in time. You can pay me money to find out that doesn't imply that. The other thing is, in German it's an adjective. And adjectives are spelled with a lower starting letter, so a lower F. But as a name, they start with a capital F. So I constantly arguing with my spell checkers, whether they are right or I am, because it depends on the context, and they seem not to guess that, whether the capital F is correct there or not. So maybe spell checkers improve at some time in the future, but it's hard, and it's also hard in other languages, like in C++, and this should be the motivating example. I give you this here, and I give this out when I teach classes or give trainings. I have this my_type thing here, I create a variable of it called I, brace initialize it, increment it by 1 with a post increment. And then I tell my students, well, that's probably not so good. You should use a pre-increment to save you the temporary and so on. And depending on what experience they have, if they are starters, they start asking me, why? Post-increment, pre-increment, what's happening there? And where does it depend on? And I tell them, well, it's more safe to use the pre-increment because you obviously seem not to do anything with the post-increment, and you don't know if it's a trivial type or it's a class type. My type can be my own class type, it can be an alias or type there for an int. So we don't know, we have to look up the type. And if I explain that to them, then they ask me, yeah, well, but what's then the difference? And then I tell him, yeah, if it's a class, then you can have an operator overload, and then there's an operator involved. Next question is, where's this operator involved? And then I tell them, yeah, well, you know, it's roughly here, so something like this. And I can make this up, of course. I can say, hey, it looks like more like this. So it's I.operator plus plus. And of course, you have to know the 0 in the parents is always there because it's the post increment. Without a 0, it's a pre-increment. Of course, who doesn't know that? So very difficult, and I like it to be able to show people the things I'm talking about and not talking wildly and gesturing on some slides. So that's the issue I have when teaching. And there are other things. That's all right. Okay, survive the fire alarm. So there are other things, like this short example here. I have a function called max. It takes 2 parameters, and it figures out whether A or B is the greater one, and then it returns that value. And I use it in a printf, printing out whether A or B is the greater value. I use A to be initialized with 1 and B with 65,530. 65,530, sorry. Question is, number 1, what is the output of this program? 1. Of course it is 1. Because I'm comparing a signed and an unsigned, I'm getting an implicit conversion. And unfortunately, or luckily because I chose the value exactly like this, my 65K will be a very, very small number in a signed representation because the most significant bit is set to get this done. So we are talking about implicit conversions. How many implicit conversions are here in this example? I'm accepting 2 different answers. Anyone? 2, I have 3. Any other answer? Correct answer is 4. Or, let's see. So, let me introduce you to C++ Insights. This is the web front end of C++ Insights. You can use it as a command line tool under Linux, on the Mac, and potentially under Windows, but I never did personally, so it's just an executable which works. You put in your code on the left side, and you get on the right the transformation the compiler does for us internally. So it's a Clang-based tool. It uses the Clang AST, and it sees all the things Clang adds to this AST during parsing time. And with that, if I transform this, we can see, in fact, I will get 4 implicit conversions. First, in the max function, A and B are casted to an int, because we compare ints, not short ints. And then the unsigned short is casted to a short when passed to max. And of course, the return value of max itself is once again casted to an integer when passed to the printf. That's what a compiler does. That's the default view. But you can also say, show all implicit conversions. And then we will see 2 more. Because 65K isn't an unsigned short. It's an integer, not a short. 1 is not a short. It's an integer, so it will be casted. It's no big deal. It doesn't impact anything. But they are there, and sometimes we like them, sometimes we dislike them, the implicit conversions. So this is what C++ Insights can do. It can show you some of the things that happens in the background. The start of the project is 1.5 years or 2 years ago, and at this time I was preparing slides for a talk for NDC Oslo, and I intended to show some of the new C++ features and how they are working internally. And doing that, I had to go over my slides a couple of times. Take it off you for 2 minutes. Thanks so much for that frequency. So quite entertaining talk. I'm not really used to a handheld, and I will need my laptop later. So, okay, I was preparing slides for this NDC Oslo talk, and I tried to show some of the internals, how the features work. And I did it one time, and then I found a bug in the slide, so I updated it. And I did it 2 or 3 times, and for everybody who knows me a little bit better, I'm not the kind of person who likes to repeat tasks that can be automated. And so I thought, okay, I can hack up some Python script to make it do the job for this talk, but on the other hand, why not use a proper tool? So I thought, well, I can write a small Clang tool doing that job that isn't that hard, probably, and it will work in general, and I do not have to parse the C++ code. It turned out that doing that, I have to learn the Clang API, which is not that tiny, so it turned out to be a little bit longer than I initially thought, but I think after a week or so, I had a small program which was able to transform a range-based for loop, a structured binding, and a Lambda. So that's fine for so far. I was happy with that. But then I thought, well, in the end it was easy and it sees more things. So I extended it and I extended it, and it took about a year or so until I released it to the public without any idea how everybody will take it. Will they say, well, that's rubbish, we don't need it, it's cool, it has bugs. Yeah, it has bugs. So I didn't know. I released it, and so far I received a lot of promising good comments encouraging me to do further work. You can visit it on GitHub or on its online presence. The idea behind it is to have compiling code out of it, because I can test compiling code, and I like to verify that the results after transformation still do compile. The other thing for that is, if I show the examples and the code coming out would not compile, it will not help that much, because then I can make up everything and I have a pretty good imagination, so that will not help. So goal number 1 is get compiling code out of this. This is not always possible, but it's the big goal. The other thing is it should help with teaching, so it should enable you to show complex things going on, which you, in a lot of cases, do not need to know, but they are helpful. So that's one of the ideas. And of course, it's open source, so you can patch it yourself. There are some limitations, and I like to take the time to point this out. It is a Clang-based tool, I said earlier, so it sees everything with the eyes of Clang. That means that if you would run the same like program with a GCC, AST, then the result can be different. Will be, probably. You also will see differences between, this is not my talk today. You will also see differences between the libraries, whether you're using libstd C++ or libc++. You will see coming up implementation differences, which is a side effect. I'm not sure if it's interesting or not. The other thing is, because it's AST-based, you will not see any difference whether you pass in -0 or -03. Optimizations happen later in the back end. This is only looking at the front end or parts of the front end. So you will not see the optimizations the compiler possibly does. You will see a couple of easy things. From my point of perspective, not being a compiler writer, the compiler does while walking your program. This is things like constant folding, so 3 + 4 ends up being 7 initially, and some ConstExper evaluation, I believe I've seen, is also done very early. There are other things which unfortunately are not that easy to make working. And as much as I like templates, it's templates. So look at this example. I have my function template, Func here, which takes a type name T, and I have my class demo after that, and then in main, I instantiate Func with demo, the type demo. I can transform this in C++ insights, and it then looks like this. It's now getting really interesting doing this with one hand. Then looks like this, and if I do the transformation, really do it. Thank you. So if I do the transformation, you can see okay, C++ insights also gives you the instantiation of the template. And you can see another thing, and that is that I insert here this if-def saying insights use templates or use template. Initially, they are removed by your preprocessor. And the reason for this is, in this example, the resulting code would compile. But imagine that the initial code would be switched a little. If I do transform this, I can transform this, but now my type class goes first. Now I can instantiate it, because the moment I'm doing this function template instantiation, it is known. In the way it was before, here I instantiate this function template with a type which is not known at this point. And this is because I just instantiate all the specializations of a function or class template directly beneath the original template. That's a limitation there that can be improved probably, but I haven't so far. So who of you has ever seen an AST? Maybe not all of you. This is part of an AST. This is just a really tiny, tiny portion of this program. There are pages over pages over pages when you do the full AST printout. Anybody knows what the C++ program behind this is? Yes, it's not hello world, it's hello, C++, with a std cout. And the reason for this page-wise thing is that the standard library instantiates a lot of types, templates, and so on. So it's not a bad thing that's happening here. You should still use the standard library, but it makes it hard to debug bug reports I get. So I prefer if there is no standard library used, but that's just this. While I developed C++ insights, I came across multiple things I never questioned before. And what I ran into was default arguments. We all know default arguments, I guess, so that's not new. I never questioned how they work. So of course, I call Func here without an argument, and I will end up with Func being called with 23. But how does this work? Really simple. Compiler just inserts the 23 at the call site for me. That's it. I never questioned that. It may not be the biggest news, but it's nice to see that there's absolutely nothing special going on. We can write this by hand, but then we have to drag all the 23s in our code. Much easier, let the compiler do that lifting. Another thing, and that might be a topic of its own, is initialization. Just the other week, we had a longish discussion about how to name a certain function to make a shared or a unique pointer which is not being initialized. So initialization in C++ is huge, and I will not talk about the rest of this talk about initialization. This is a small example. I have 4 variables here, 4 arrays, A, B, C, and D, and they use different initialization forms. First one doesn't do anything, so everybody who knows that with C++, well, it's an uninitialized buffer. Second one uses praised initialization. There you have to know it's either 0 or default initialization happening here. And then there are 2 things coming up sometimes with my students. When they understood what line number 4 does for B, they say, hey, I like to be explicit, and I can do that for a simple int, for example. If I initialize a simple int, with the empty curly braces, I get an initialization with 0. I can also initialize this particular int with 0 in the curly braces. So I like to be explicit here, and I like to state that my variable number c should be initialized with 0. And the sad part is c seems to work, because it does the right thing. And there are other people saying, well, zeros are all over the place. I like a different number. I initialize my variables with 77. I personally prefer 0xAF, but that's just because my initials match there. So question is, what happens to all these things? And it may not be the biggest reveal to you, assuming, but consider you're teaching this to newcomers in C++, then you can see, okay, if I do the transformation, A is uninitialized, easy peasy. B, on the other hand, we get the 0 initialization here for the equivalent of the jar. And then C becomes interesting because the first element in the array looks a little bit different. You would see a static cast here if I hook up all the casts. But all the other values are the default for a jar. So it looks like the same, and the result is the same. Your buffer is initialized with 0. So you get the impression you know what you're doing here, and then you're switching to variant used for the variable d, saying you want your entire buffer initialized with 77. And you somehow realize, oh no, it's only the first element, which makes sense, of course, because how would you like to initialize the remaining elements if you have more than one? So this is a problem I sometimes come across, and now can show it to people. And in my experience, if you are able to show something to people, they understand it better or take it easier. Next, in-class member initialization we got with C++11. I have my class init here. It consists of 3 variables, a, v, and s, an integer, and std vector of int, and a std string. And I use in-class member initialization to give them default values. And I use the default constructor to assign I a different value, in my case 9 instead of 0. So one question is then often, do I end up with 2 initializations for I? Because one time I set 0, the other time I set 9. And the other question is, and how does this entire thing work? Let's have a look. If I do this transformation for the code on the slide, then I can see, first, of course, I'm getting only one initialization. It's C++ after all, right? So in the transformation, I don't see the 0 anymore because I gets initialized with 9. That's what I requested in the default constructor. And then we can see that my default constructor now has 2 more elements it initializes in its initializer list. And this is my std vector, which gets the values 1, 2, and 3, and my std string, which gets the value hello. So it's syntactic sugar, making it for us easier to write the code on the left, while we would be able, and sometimes still do, write the code on the right. But the compiler does the transformation for us. I really like that. It's easier for me to write the stuff on the left. Lambdas are another topic often requested. How do lambdas work in C++? I have this const array hello here. And that says, hello ACCU Belfast. Okay? And then I have this lambda capturing that string by reference and using a printf to print it out later. And it is directly invoked. So what is behind this? It's quite interesting. So lambdas are a class. The compiler makes up for us the so-called closure type. So I have to invent a name here because the compiler doesn't bother to give that thing a name. It doesn't need a name for it. So first of all, it's a class. And then there's the interesting thing here. This is the call operator the compiler injects for us in this class. And it contains the body of the lambda I wrote on the left. And of course, the compiler further takes care of whatever I did like to capture. In my case, it captures me a reference to a const char array of size 19. And then it initializes that thing, and below here, this is the invocation of the call operator. And we are done. So I really was surprised the first time when I come across this, because it's so easy. I have done it probably a couple of times in C++ 98, and now the compiler gives me the abilities to do it with shorter code, nicer syntax. I really like that. Lambdas are one of the things, I don't know how many are there, which got updated with each and every standard we had since 11 so far. So with C++ 14, we got generic lambdas. Generic lambdas means that I can now have a lambda which takes an auto parameter. At this point in time, it's the only place where you can put a single auto in a parameter of a function. And what this does in the background, look at the call operator. Our call operator has now become a function template or a method template. It takes one parameter of type name something, and with that I can instantiate that lambda and specifically that call operator, as we can see below here, with different types. Once with double and the other time with end. So it's a, at least to me, easy looking addition. Not sure how hard it was to implement this in the compilers. But it gives us another way for writing generic code, which I think is highly valuable. This might not be enough. So with C++ 20, we will get another evolution of the lambdas. There we will have templated lambdas. And they solve a problem illustrated here. Generic lambdas are great. They enable us to write generic code. I once again use this max function for illustration. So I have a lambda here which takes two variables, x and epsilon, and once again tries to figure out which one is the larger one and returns that. So I can call it as shown here with either 2, 3 or with 2, 3.0. Both work, both compile, it's fine. But the second one is probably not what I want, because what is my return type? My return type this time is double. Probably or not. So I'm giving mixed types in here, and I like to have a way to express that this max lambda should be called with only one type. Okay, and I cannot express that with the auto generic lambda we have in C++ 14. So in C++ 20, we finally can put the angle brackets in the lambda, saying, okay, this is now a templated lambda. It takes, in my case, a type name t, and both parameters are of this type t. And now the second line stops compiling, because now we have a template, and the rules for templates are there are no implicit conversions. So the compiler says, no, please either cast it in some way, or you have a bug in your program here. So this is great, and at this point you might be able to guess how this looks internally, because Clang 9 recently implemented this. You probably don't see a difference to the generic lambda, because it's simply just the call operator, which is now a template. The nice thing is, and I don't have examples for that here with me today, we are no longer limited that it needs to be a type. It's a template. So we can also use non-type template parameters there. Let's say that my Lambda should take a std array of type jar, but of a variable size. Size depending on whatever std array of type jar you're passing in. So this gives me a whole new way of working with Lambdas. In the evolution of Lambdas, I didn't mention one tiny thing. I don't know how many of you used it so far, relied on it. With C++ 17, Lambdas became implicitly ConstExper. So the compiler adds for us ConstExper to the call operator of the Lambda. And why is this worth mentioning? If you look at this example, then we can see this is the implicit ConstExper the compiler adds. And the reason why this is shown as a comment in C++ insights is at this point, neither I nor it seems the compiler knows whether this function is really ConstExper or not. Because the compiler adds it implicitly. It can remove it later, in a later stage of compilation, when it realizes, due to evaluation of the function, ConstExper evaluation, that it in fact is not ConstExper. So, for example, if in the same example I would use something like a printf in here, just doing nothing, just being there, then the compiler still doesn't know in the front end, or doesn't tell me at least in the front end, whether that thing is ConstExper or not. It knows it's C++ 17 mode, so add a ConstExper to make it eligible for ConstExper evaluation later. And to my understanding, when ConstExper evaluation then is done, the compiler sees, oh, there's a printf in there that cannot be ConstExper. I remove that, because telling the user to remove the printf doesn't help. The user has not put the ConstExper here in the first place. So here I cannot reliably show whether that thing is ConstExper or not. But what you can see is, did you see nothing? Which is not the intent. Oh, we are back. So you can select the modes. Here currently it's C++ 17 selected, and once when I switch to 14, you will see that the ConstExper in general is gone, because in this mode the compiler doesn't add the ConstExper. So C++ Insights in some cases also helps you to see what changed between the standards, and sometimes it may help you to catch a bug because you did something like, you know, that switch from C++ 11 to 14 when ConstExper members no longer being implicitly const, things like that. So it can help there. So what else do we have? Sometimes it can be pretty hard to get a type right, at least in C++. In other languages like Python, I do that mistake over and over again, but it doesn't care. It's just an int, which was before a string. In this example, I have a map consisting of a jar, of an int as a key, and jar as a value. And I give you 4 different versions, 4 for loops, range-based for loops, iterating over this obviously empty map, but imagine it would be filled with some content. Which of these versions does the right job? Just give me a number from, let's say, 0 to 4. You can either tell me which one or how many. I asked to make it easy for how many, and we will then figure out which one, but if you like, you can also say which one.
The second is correct.
The second is correct. The third is correct. The fourth is? The fourth is correct. So, summarizing this, we are saying that only the first one isn't correct. And of course, you're probably experienced with C++, and you have looked this up. Maybe it has bitten you in the past, because for learners, it might not be that obvious, because I'm instantiating a map with an int and a char, and it seems reasonable to say that I like to get the elements out there as a pair of int and char. So let's see. Don't bother with this implementation. I tried to get rid of all the extra things the standard library does, but it's more or less what the standard library does. So when I do the transformation, we can see one additional thing, and that is the transformation of a range-based for loop for all those of you who were not familiar with this before. For range-based for loop, the compiler first opens up for us a new scope, and it puts 3 new variables in there, range, begin, and end. It assigns them values, and then it uses a regular for loop to iterate over all of the elements. We can see here it uses the operator not equal, and of course, you know that by now at least, it uses the pre-increment operator to increment the iterator. And now, if you look at what we are getting out here, we can see this is our range variable t as requested here on the left. And this is of type pair int jar as requested, as well as here. But we can see that this thing here, it looks like a construction, which is what we are getting here. So we are facing an implicit conversion, which is the thing we liked probably before, but in this case not. We are getting an unnecessary copy for my trivial types here that may not be matter, but let's say you have a map consisting of all the Lord of the Rings books and all of the Game of Thrones scripts. So then the stood strings behind it may be bigger, and it may matter whether you're copying them or not. And so far you have been right. The first one is the odd one. And for the second one, we can see, okay, it's just dereferencing the iterator and assigning it so to the reference. There is no copy. The same goes for the third version, which uses auto. And I'm not sure if it's the most correct one, but it gives me directly the variables key and value, k and v in my example. This is also correct. I'm just, as you can see here, assigning the value of the iterator to the reference. So it helps showing things like these and showing why the first one is, in fact, the odd one. I like range-based for loops, so I would like to highlight that before I go to the next slide. They're great, but they also have some issues. Look at this example. I have this struct called keeper. It has a std vector in it, which I initialize with 3 values, 1, 2, and 3. And it has this function items, which returns a reference to the data. Below there, I have another function called get, which just returns by value such a keeper struct and is happy. And then I'm using the range-based for loop to iterating over all the items in this vector, saying get to give me such a keeper thing, and then dot items to get all the items in that thing, and iterating over it. Question, what's the output of this program? Correct. every answer is the right one. It's undefined. And the reason why it is undefined, I can show you. The reason is here. We are looking in the range-based for loop and in the internals of the range-based for loop. And as we can see, here is my call to get dot items. And the return of this thing is assigned to the range variable. And this is a reference, and it's not a const reference. And even if it would be, it wouldn't change that much. So effectively, the moment I'm trying to access the elements of items, I'm looking at a dangling reference. They are gone already. So whatever answer you would give me before, UB is the most correct one. The program can't print out anything. I tried it a couple of times. One time it printed nothing, nothing, 3. The other times nothing, 3, 3. So you can have quite a lot of fun with that. There are ideas, I think, to maybe adjust this a little in a broader sense, but till we come to that, maybe with 23 or later, we can look at C++20. And C++20 comes with range-based for statements with initializers. And this is neat. Now I can say I have a range-based for loop, and it takes an initializer. It creates a new variable items of type autorefref, and there I call get. And now, in the rest of the range-based for loop, I can say items dot items. Sorry for the bad naming. Naming is hard. I can now safely iterate over my items. And if I once again look at C++ insights, and how this is transformed, then I can see, okay, once again, it's really simple. I request a new variable inside of the range-based for loop on the left, and so I get it. It's the first thing when the scope is opened, the variable I requested is inserted there, the call to get, and now I have an R-value reference to items, and then below that, the range variable is initialized with items.items as requested. Now I can make this range-based for loop safe. There are other use cases for that. This is one I came around frequently. I had a range-based for loop. I said I liked them, I really do. But this one thing bothered me. I sometimes had a case where I did like to iterate over a container, maybe vector or something else, print out the values of the elements, but with some annotation, for example, an index, at which position in the vector they are. And doing this pre-C++20 required me to put this index variable outside of the range-based for loop, and with that leaking in all the adjacent scope and all the following scope. And this is something I didn't really like. Of course, I can make up my own scope, but that's not so nice. So now with the range-based for loops with initializers, I can also put this variable just inside the range-based for loop, and the variable idx will be visible and usable only in this scope. So that's a nice addition, I think. C++20 on 17 changed a couple of things for templates. What I'm showing you here is a version where you can use auto as a non-type template parameter here, which is initialized with the default value to containing a space. And then there's a variadic template, so it can be instantiated with an arbitrary number of types. And what it does is it just prints out all the types, each separated by the separator value. It uses the ConstExper if, as you can see below, to do this expansion only as long as there are remaining elements in the pack. So it does a recursion here. And looking at this from, or at the internals of this, we can see here, okay, this is our base template, our primary template print. And here at the first instantiation, the 32 is the decimal value for our space. And then it takes two parameters, char string of size 4 and a char array of size 6 and then 4, and then an int. And here we can see the ConstExper if. The compiler at this point, of course, knows the size of the pack. It's 2. That's why I can print it here. Then we see the next instantiation of this print. It now has only 2 parameters, jar and an int, and the pack size, as we can see here, is reduced to 1. And then in the final print version, it's only the first or the single parameter outside of the pack this template takes, and my ConstExper if, it's still there, but it contains nothing, so it will be removed later in some of the optimization stages. So this is one way how we can write this. A totally other way, or not totally, but slightly other way, is doing it together with lambdas. And what we got in C++ 17 as well is fold expressions. So what I have here is the same base, the primary template. It still does the initial cout, and then it has a lambda. It's a generic lambda, by the way. It takes not a parameter by reference. And then here, I do have my fold expression saying, call my lambda with all the arguments and separate these calls with the comma operator, which is a really good use case for the comma operator. If you ever wondered what you need the comma operator for, it's things like this. If I do the transformation, we can see there is now only one larger instantiation this time of the print function. So no recursion, of course, is happening. I haven't requested any. I have my lambda here, which is the class, which, because it's generic, has the templated call operator. And I have instantiations for the char array of references of size 4 and to an int reference. And below here, we can now see the lambda is invoked for the first argument, then the comma follows, and then it's once again invoked for the second argument. I sometimes get a question which of these two versions is more efficient, and I don't know. I really don't know. Specifically in this example, I think in the first version, the print will probably be in line because it's really short. It doesn't do that much. Sometimes people fear the recursion and the resulting code. Then maybe use that. I'm not sure which one is really more efficient in terms of either a code space or speed. So we covered this. What else is to say? If you like the project, you can support it in multiple ways. You can, of course, before you support it, start with using it and liking it. That's great. If you are at this stage and then you like to support it, go to GitHub. File an issue report. Yes, that's support too. At least I consider that a support. There are a couple of which are still open, and I try to close them. You, of course, can also pick one of the issues and send me a PR such that it's fixed. You can also send me a PR with new features, of course. You know how GitOps works. If you like to give money, your money away. Everybody asks for money, so it's fine. You can go to Patreon and support it there. It's just to get the infrastructure or keep the infrastructure running. And if you like to get something in return for your money, you can buy yourself a t-shirt on the Spreadshirt shop. So that's another option. Some time ago, I tweeted about another feature I implemented in C++ Insights, and as a reply to my tweet, I got this one, and I don't know the person. He or she seems to be at least aware of German, because the question is, so it is completely fertig? No, it's not. I can tell you. There are a couple of things with C++20 that needs to be added, and we will probably add more stuff in C++23, so there's still work to do. It still maybe has some shortcomings or some statements which are not supported, so probably there will be some further development on that. With that said, I did not mention, I just realized it once again. I'm German, I told you that in the beginning, right? And my last name is Fertig, so you might think that you can trust me pronouncing that word, German. You shouldn't. It took myself roughly 30 years to realize that I mispronounced my own name. Because from where I'm coming from, it's perfectly fine to say Fertig. It's hard K at the end, or hard G. But in proper German, it's pronounced Fertig. All right? I'm doing this wrong all the time, even after so many years. It's a little embarrassing, but, well, it's a language, and I have bugs in my C++ code as well, so why should I get my own name right, correct? So with that, there are only 3 more words to say. I am fertig. Thank you. Do you have any questions? We still have a couple of minutes left.
Quick question, Andreas. Whenever you talked about not seeing the const expression in the C-lang AST for C++17, did you determine that yourself? Or write the comments in, or what was it that the CPP Insights tool was able to see that allowed you to display the const expression comment?
Okay, so the question is, I talked about the C++17's edition of Lambdas, the implicit ConstExperness, and the question is how or where do I see the ConstExper that it's coming from? And maybe I was not clear there. It is in the AST. I see that it is marked or labeled as ConstExper. The thing is, as I tried to show you, it is also there if there is an obvious statement in it which makes this function non-ConstExper, like the printf example I gave. And at the point in the front end, I can look at with C++ Insights, the compiler says ConstExper. And I need to do ConstExper evaluation, so I know a couple of ways for variables to force Clang at this stage to do a ConstExper evaluation, tell me the result or tell me that it doesn't work. But I think it's too complex for this function invocation. So this happens later in the back end somewhere, and then I think Clang just rips off that implicit ConstExper, which it deliberately added because it doesn't make sense at this point.
Got it. Is that to say that whenever the comment was displayed, it was as much a guess as anything else? You
can say so, yes. I try to give you the correct versions, but to be fair, maybe the ConstExper case can be improved. So I may add the commented ConstExper even for constructors. Other questions? Yes?
In the UI, where you have 2 panes showing the original source and the allocated source, do they synchronize with each other? If you click on one, it'll show you the matching.
Unfortunately, it's not got bold yet. There is an issue open, and somebody suggested doing that, and he also or she also volunteered doing that, but I haven't heard back. And I thought about it myself for a while. I am not sure how easy it is, because imagine for templates, I generate a whole bunch of code, so a regular div will not do that good. I have a private version where I tried to annotate the output with the source lines and columns where it comes from. But then it means that I have to parse it for the web representation, and I haven't had time to do that, and I'm not sure if it's really doable. I think it would be worse, yes. You're welcome. There was another hand.
Can you see the actual output of the program?
Can you see the actual output? Oh, no. It's not executed, the program. But there is, I should have mentioned that, should have asked for that, usually I do. There is, somebody added that. There's a Compiler Explorer button. If you click on that, it will open a new Compiler Explorer tab with the source code from the left in it. And there's also a button at Compiler Explorer which links back to C++ on sites. So it's not completely perfect, but at this point it does. Yes?
You mentioned something about the CLI version. Or was it, did I misunderstand?
The CLI.
Interface to run the translation to get output to a file, or is it only on web?
No, it's in fact what this thing does is invoking a Docker container which has the tool installed. So you get a command line version of it. That's the default. You can download it for Ubuntu on the GitHub page, and for Mac you can build it yourself. There's also a Windows version recently, but I haven't used that one. So it's a Clang tool, like Clang format, like Clang tidy. You can invoke it from the command line, and you will get then the output to stood out.
Okay, so you can also like get includes and everything, so you can have a bit larger program if you're wondering if default parameters are fetched from the header file or if it's used from the CPP file.
So question is if you can use it in a larger context. Is that if you have local includes and maybe confidential includes, something like this? Yes. So the question to that is yes, you can invoke it from the command line on your own machine. Because it's a Clang tool, it's sometimes hard to teach it where the includes are and where the system includes are and things like that. I had a couple of issues with that, but in general, if you use -I, capital I, and then path to your includes, then it works. I also once had a wrapper script which you can hook into a Makefile, and it replaces the GCC call, for example, with a Clang insights or C++ insights call. It's a little bit guessing where the parameters go. So, but if you like to know more, I can show you later an example. So it definitely works. I used it with larger source code than just a couple of lines. You're welcome. More questions? Yes?
I guess it's a broader question, with ConstExper becoming more prevalent throughout the language. I guess ordinarily I have runtime debugging. I can use DTB and step through my code. How can I debug ConstExper code at compile time?
So the question is, how can one debug ConstExper code at compile time? And probably this is a good question for WT21 when we next meet, because yes, you're right, there's more stuff going on in the ConstExper world, and it would be reasonable to have a way to debug that. I know that there is a GCC patch, an unofficial one, which adds a static print to it. Jason Turner in his C++ Weekly had an episode about this. It's from the same person, but I can unfortunately not recall the name, who is currently implementing Clang concepts for Clang. And I think he did that because the static print was a dead end, and he tried to get better error messages from the concept, so you still will not get the debugging there. I have no good answer. Other than that, if you're interested, the patch may be still out there to hook up that static print. Maybe that's enough for now. You're welcome. Anything else? Then it's time for the break. Thank you.